Hello and welcome to this recorded learning on power planning for your FPGA device. My name is Frank Nelson. I'm a Xilinx technical trainer and course developer. I will be your instructor for this module. In this module, we will learn how to sufficiently power your FPGA and answer some common questions. Our objectives for this module are to explain how static power is different from dynamic power, describe the impact of smaller device geometry has on static power consumption, define the relationship between leakage current and junction temperature, and describe some of the device datasheet information that pertains to power consumption. During normal operation, the total power required for your FPGA is your static power plus your dynamic power, but this excludes the power necessary during power up and for minimal operation. We will talk about that in just a moment. The key is to understand that your static power is greatly dependent on your device's transistor leakage current. This is simply the gate-to-substrate leakage current, and this is required for all the transistors used in the FPGA. This includes CLB logic, DCM resources, block RAM resources, and other CLB logic functionality. This static power can be thought of as core power. Dynamic power is dependent on the switching frequency of the various resources a designer ends up using, and as you can imagine, since there is a lot of logic, this can be a large calculation, particularly since not every resource is toggling at the same frequency or all at the same time. In fact, during normal operation, this can be the most critical element to an accurate power estimate. This slide points out that newer devices use smaller transistor lengths to improve performance, but this increases your system's power consumption. As these transistor lengths get smaller, the source and drain current increases quite a bit. Faster transistors have a low threshold voltage associated with them. These low voltages also demand a small gate oxide thickness, which adds up to a higher leakage current. To help users resolve some of these issues, Xilinx has introduced new features such as suspend and hibernate modes, which allow an FPGA that is not operating to retain its state and effectively shut down until reactivated. Another interesting property about leakage current is that if you increase the environmental temperature, the leakage current goes up exponentially. Now this is a very normal CMOS behavior, but with smaller geometries, the extent to which this curve becomes steeper at higher temperatures gets worse. So it is very important that you manage the temperature of your device by whatever means necessary. This may require the use of fans and/or heat sinks in any FPGA application. The key is to manage your power so that you never get to this nightmare. There are ways to design for low power and manage your system so that this never becomes an issue. But most of all, don't fail to estimate your power consumption and then not plan your system power consumption. This slide shows the internal minimum current required to power the core of the Vertex 6 FPGAs. This current characteristic is just one of the 3 voltages necessary to power the device. The currents necessary to drive the VCCO, which is the I/O power, and the auxiliary power source, are also described in the datasheet. All 3 of these currents are required to determine the minimum current that your power supply should be able to provide for your design to operate normally. Note that using just this information does not guarantee that your design that you have programmed into the FPGA is going to work successfully. This is just one part of the static current required by the FPGA. After configuration is complete, if your dynamic power consumption is excessive, you will still need a larger current source. Please refer to the Spartan 6 and Vertex 6 device datasheets for more information. This slide shows a chart from the Vertex 6 datasheet that shows the minimum current required to power on a Vertex 6 FPGA. What you see here is how we specify this requirement in the DC characteristics section of the datasheet. All of these currents are required to determine the minimum current that your power supply should be able to provide to power up the device. Note how each is defined relative to each current's quiescent current. In fact, the device requires more static power at power up than static power during normal operation. Using just this information does not guarantee that your design will operate properly, just configure properly. It is up to the user to plan on how much current their system can use, and of course this is dependent on the design, FPGA, and other devices that are used in their system. It is also up to you to anticipate how much your worst case power consumption might be. Now we provide descriptions of the current draw your FPGA might have at power up or during minimal operation, but we don't provide information on worst case conditions. Simply put, too much is design dependent. That is dependent on the resources used, the clock frequency you run on, etc. So to get the best power estimate, we offer a couple of power estimation tools that you should consider using. So I'm going to point you to that power estimation REL to learn more about that. Power estimation can be performed at 3 distinct phases of the design cycle. At the concept phase, we recommend the use of the Xilinx Power Estimator spreadsheet. This allows you to enter in some rough estimate of the resources that you plan to use about your design to get a good power estimation, but granted very early in the design process, so very little detail is actually known about your power. At the design phase, we recommend the use of the X-Power Analyzer, which uses your completed, placed, and routed designs. So all the true information, all the device resources, all the routing that's necessary for your design is known. So this power estimate is much better than the one you would get with a Xilinx Power Estimator. And finally, of course, you can go to the lab after you've built your FPGA and program the FPGA and do an actual test with instrumentation in the lab to determine your actual power used. In summary, static power is dependent on the transistor leakage current. Dynamic power is dependent on the switching of the logic in the CLB array and the ILB resources used. Smaller device geometry increases the static power consumption of all devices. Newer devices will have a higher static power consumption, and this is something that surprises a lot of people. An increase in junction temperature dramatically increases the leakage current and your static power, so it's important that you manage the temperature of your environment of your final application. The minimum current required to operate and configure the FPGA is provided in your FPGA's datasheet, but the best way to estimate your power consumption is with either the Xilinx Power Estimator spreadsheet or the X-Power Analyzer utility. Well, there are lots of ways and lots of places to learn more about FPGA power consumption, and they all start at support.xilinx.com. In particular, I want to point you to the Spartan 6 FPGA Power Management User Guide. This discusses a lot of the concepts we discuss in the other recorded e-learnings on power management, including introducing some of the newest features such as suspend and hibernate modes, and describes the necessary voltage supplies, describes the low power devices that are available to you, and describes power on, power down behavior as well as power estimation options. So check it out. If you would like to see what other courses we offer or what other free RELs are available, go to the Xilinx education link you see here. We also encourage designers to consider attending the Designing with Spartan 6 and Vertex 6 device families. This will help you get the most out of your FPGA design and optimize your design for these architectures. We also mentioned that we have a number of power RELs that are also available to you for free recordings, such as how to plan the power for your FPGA system, power estimation, and learn more about the Spartan 6 and Vertex 6 power management features. My name is Frank Nelson. You've been listening to the How Do I Plan to Power My FPGA recorded e-learning. Thank you for listening, and thanks for your business.